This is all you need to know about Newton's laws on one whiteboard. So listen up. We can write them in algebra, and it's a useful way to remember them as this algebra and these little diagrams. So this is Newton's first law, and it deals with pairs and forces that are equal in size. So Newton's first law states that if there's no resultant force, then there's no acceleration. That's what this says. The sum of the forces is zero, then the acceleration is zero. So it doesn't change its motion. It's not about whether it starts or stops. It's about whether it changes motion. It accelerates, either speed changes or direction changes. And if you think about this, a free body diagram is two forces on one object. Those are equal in size, but they're opposite, so they sum to zero. Now, Newton's first law is kind of contained within Newton's second law. We could kind of get away with just Newton's second law, actually, because if the sum of the forces was zero, then one of these two things would have to be zero, either the mass or the acceleration. If we're talking about a mass, then that's not going to be zero, so acceleration would be zero, right? But Newton's second law is the situation where there is a resultant force. So one force is larger than another, again, on one single body. So it states that the sum of the forces, the resultant force, is equal to the mass times acceleration. In other words, it's proportional to mass, it's proportional to acceleration. If you were to double the force on a same mass, you'd get double the acceleration. And the force needed to get that acceleration is also proportional to the mass. So that's Newton's first and second law. They're dealing with forces on one body. Newton's third law deals with action and reaction pairs between two bodies. So that's why it's different. That's why it's useful to remember this little diagram and state it in this kind of way here. The force from A to B is equal but opposite, that's the minus, to the force from B to A. So you can see here clearly that there's two objects, and it needs to be two different objects for Newton's third law to be involved. And you can see that each one of the objects only has one force on them. So there is a resultant force on each object, so it can accelerate. That's where people, I think, get confused with this idea, but equal and opposite, they get confused with this Newton's first law pair. Okay, so the diagram helps you hopefully see there's a real and serious difference between Newton's third law and Newton's first law. There is some conditions for Newton's third law, okay, which is that it must be different bodies, it must be the same type of force, it must be equal in magnitude but opposite in direction, it must last for the same time, and it must follow the same line of action. That's really all you need to know for Newton's laws, okay? It's just then about applying them to different situations and making sure you quote them fully and you don't have any misconceptions that a lot of people do about Newton's first law, for example, which is that they think it's start moving or stop moving. Or Newton's third law, for example, they think Newton's third law always results in no resultant force. Let's state it like this. Let's say a boy pushes on a wall. Boy pushes on wall, therefore wall pushes on boy. You can hear that wall pushes on boy is the only force on the boy. Therefore, there is a resultant force on the boy. Therefore, he can accelerate. Thanks for watching Good at Physics. Stay tuned.